So for these, so if you remember the way we represent them is that you have your states. For example, you're going to show these arrows where you can jump, for example. But there are no self jumps because you are showing there is holding time, which tells you that when does the jump occurs. So this is a Poisson process. That means you have exponential probability distribution. And this process itself, you describe using these transition probabilities, which you combine in the transition matrix, which we build up by giving these ij, which is built up of lambda I. This is the time to stay this is the exponential parameter that controls stay in state I. So it's telling you what is the probability that when you will jump out of the state I, and this Pij is then the discrete jump probability, discrete chain jump probability. So it's telling you that when you jump, where do you jump? Which state has what probability? Like you jump from I to J or K or L or M. Now, what you have is, so this is, and if you recall that this one, so out of these are the transition probabilities. And you write lambda II equal to sum over the rows, and this is how you compute the diagonal entries, and then this G matrix is just this lambda ij matrix. This is the transition matrix. So for example, we had, this is all review, that you have a two-state system, 0, 1, and you have this probability lambda, and you have this probability mu. This is lambda is the weight, and similarly mu is the weight. So in this case, G is simply lambda and mu, and then you write minus lambda minus mu to complete the transition matrix. And if I'm given the transition matrix, example, you're given this, you have 3 states, 1, 2, 3, and you're given this matrix. So you can check that the way it's built, you have to sum each row to give you a 0. So 4 plus 2, 6. So that's why you put a -6 here. And on this diagonal, you put a -2. In this diagonal, you put a -4. So on the diagonals, you will have negative terms. And on the other entries, you will have positive terms because those are probabilities. And diagonal is there to make the row 0. Now from here, I have lambda 1. I can compute the holding times because each of these is just this. And these discrete jump probabilities are just these. So therefore, lambda 1 is 6. And what it means is the expected holding time is 1/6. And so on. And P12, probability, discrete probability of jumping. When you get out of the state 1, where will you jump? The probability of jumping into state 2 is 3. So that's the main structure of this transition matrix in this case of continuous time. Now we then discussed various theorems, and essentially our main result was that just like in case of discrete processes, this gives you is the condition for stationary distributions. And because of how these continuous processes are described, all you need if the chain is, if the discrete chain is irreducible, then you have, this is enough to conclude that you will have a limit distribution which will be same as the stationary distribution. So things are, in a sense, much simpler because of the way you describe them. Now, one class of these models is the birth-death models, birth-death processes. So what is this process? This is a process where if the discrete chain is a random walk. Then the process is called a birth death process. So what do I mean that the discrete chain is a random walk? I can write the same thing in this way. The only non-zero uh, entries in transition matrix are you can just take one step forward or one step backwards. That's why I'm saying that the discrete process is a random walk process. So, for example, something like this. You have these arrows, and then you have these arrows. Some of them may be even zero, but these are the only ones. You don't have a double jump or any other arrow. So why is it called a birth death process? Well, essentially, you can think of it as these numbers as some population. So consider the numbers as population. So if there's a new entry into the population, if there's a new birth, then you make a population increases by 1. And if there's a death, decreases by 1. That's why you have these single jumps. So these are called the birth death processes. So for example, if I consider a population of cells and each cell lives for a certain time described by exponential distribution alpha. So alpha is the parameter for its lifetime. And then either it splits into 2 new cells with probability P or dies without splitting. Then the probability of death is 1 minus P. So after an average time 1 over alpha, it either splits into 2 cells with probability P or dies with probability 1 minus P. So on average in time 1 over alpha is trying to split, but it succeeds with a probability P, otherwise it just dies in the process. So then your random variable is the population. Then X of t is the population, number of cells, and your state space is 0, 1, 2, and so on. Now, how would you write the transition rates for this? Now, the thing is that if you have, we have to write, we need to give these entries. And if you look above, what is gonna depend on? The parameter of your Poisson process times the probability of jumping into a particular thing. So we know that if I write, I have to give this. So I will have, all of these will be 0 unless I have this thing. This will have P here and some parameter here. We have to figure out what parameter comes here. Similarly, this will be non-zero. You die, and it will have 1 minus P and some parameter here. Well, actually, these two parameters will be same because it waits for same amount of time before taking splitting into two or dying. So only these discrete jumps are different, but these holding times, they are going to be same because these holding times depend on this thing, not on this. So what's the holding time over here? Well, suppose so we are building this kind of a thing. Suppose we have I cells at a given time. Now, each one of them has an exponential distribution of lifetime. Any one of them can split into two or die. And we are looking for, so when any one of them does it, we take a jump here or here. Take a jump by one number if any one of them dies or splits. And each one of them has an exponential distribution with a parameter alpha. So how do you find then is the distribution for the jump? What is the parameter for the jump? So for this, so suppose you have n variables with each of them given by some exponential distribution. I want the order statistics. For x1. So the first order statistics. All of these x1, x2, x3 up to xn, they take certain values randomly according to this distribution. And out of those values, I pick the smallest. This is the smallest. So my question is, what is the distribution for the smallest value? What kind of distribution that is going to be? So I can build up the distribution by noting, I can say that x1 is going to be greater than x if and only if x1 is greater than x, x2 is greater than x, all of them are greater than x. So therefore, my probability that any smallest of them is greater than x is equal to probability of x1 greater than x and x2 greater than x and so on, all of them greater than x. And that is defining for me disorder statistics, that the smallest of them is still greater than x. And since it's an and, so I can split it into a product because they're independent. And each one of them then is this. So that means that when I have n variables and each one of them is exponential, here I had assumed that they have different parameters for the exponential distribution. But when if the parameter is same, and I'm looking for that when does any one of them splits, then the exponential distribution, this implies if I have, I was saying if I have I cells, then the distribution for any one of them splitting or dying is exponential with parameter I alpha, because the single parameter was alpha and I am summing all of them. So I get I alpha. So therefore, this thing over here, I have to put I alpha. Similarly, I alpha here. In other words, this is my lambda I. So lambda I is I alpha. Now, people define birth weight this jump probability is called the birth weight of the ith population number, and death weight is mu I is the death probability over here. So, and in this case, the birth rate, what we have found is iota alpha p, and this is iota alpha 1 minus p. Now over here, you can see that I can, because of linearity in I, this is linear in I. So I can define, therefore, I can define individual birth rate or death rate. Because if there's a birth rate of I alpha p, then I can interpret it. It's because I have I elements here, and any one of them can give a birth. There's a weight associated with each one of them, and I'm getting I times alpha p. So individual birth rate is then alpha p, and individual death rate is alpha 1 minus p. So in general, if you have this guy equal to I lambda and this guy equal to I mu, these are called the linear birth and death processes. Then you can call these lambdas as the individual birth rate, and similarly this guy is individual death rate. So what we have then describing this cell population is transition matrix can be described by giving these probabilities. If you are zero population, you can do this is an absorbing state. If you are at 1, then you have a lambda, which is equal to alpha p. This is 2 lambda. This is 3 lambda. And this lambda alpha p is for this process, but in general, you have, if you have this linear kind of process, then you have lambda, 2 lambda, 3 lambda, and so on. Similarly, on this, you have 3 mu, 2 mu, and well, wrong. This should be 4 mu. This should be 3 mu, 2 mu, and mu. So this is the transition matrix for it. And if you want to write it, it's 0, 0, 0, 0, 0, mu, lambda, 0, 0, and this guy by the rules is this. Because when you are at 1, there's a probability mu here, going here, and probability lambda going here. Then you have 0, 2 mu, 2 lambda, minus 2 lambda plus mu, 0, 3 mu, 3 lambda, minus 3 lambda plus mu. So this is the general structure of these linear birth and death processes. And one can analyze this by giving different lambda and mu. Let's consider another kind of process and build the matrix for that example. So suppose you have a population with death, individual death rate mu. So at any time, any person can die with a death rate of mu. So it's a Poisson process. There's an exponential distribution, and anyone can die with an exponential parameter equal to mu. Then, but there are no births. Instead, there's an immigration into the population. So randomly, people join the population. So immigration is the Poisson process. With exponential parameter lambda. Lambda is the rate. And mu is the death rate for individuals. So this means that even if I start from zero population, I can take a jump because someone can join through immigration. If you're at 1, again, you have a constant rate of immigration into the population. While if you are here, you have a rate mu of dying, but this rate, just like in the previous example, is twice because you have 2 people. So both of them have a rate of dying. And as we proved that when you have 2 persons, when you have n persons and they have an exponential distribution of something happening, you have n variables, then and you are only counting when the first event happens. That's again an exponential distribution, but with all the parameters added. So that's why you get a 2 here. And you get a 3, you get a 4, and so on. So what you have, essentially the difference is from the last example, there mu I, the death rate, the total death rate at the ith population level was I times mu. And it's same over here, where mu is the individual death rate, but lambda I is lambda. So you can think of it as a birth rate, but it's a constant, no matter where you are, what number you are, because it's a constant immigration flux. It doesn't depend on how much population you have. So if I make the matrix, I have gamma 0, 1, which is lambda, this thing. And by the rules, gamma 0, 0 is minus lambda. So on. Gamma 1, 0 is mu. Gamma 1, 2 is lambda. And this by rules is this. Then I have 0, 2 mu. This stays lambda. Minus lambda plus 2 mu. 0, 0, 3 mu. Minus lambda plus 3 mu. This is lambda. And so on. Now, this guy, by the way, when does this class end? 9:30, is it 10:30, right? That's what I know. Yes.
Yes, sir.
10:30, right?
Yeah.
Okay. So this is clearly the chain is irreducible, and we can find the limit distribution by simply finding the stationary distribution. So all you need is this thing. I wish I could just copy it. Maybe I can. Zero, zero, zero. So this gives me, now these things are becoming kind of standard. Plus mu phi 1 is 0. So this gives you phi 1 is equal to lambda over mu phi naught. And if I look at the next equation, that gives me lambda phi 0 minus lambda plus mu phi 1 plus 2 mu phi 2 is 0. And then I put this thing over here. Phi 1 is lambda over mu pi naught. And when I solve for it, I get, after a little bit of cleaning up, phi naught. And I can keep doing it. For example, if I do the next one is lambda phi 1 minus, if you look over here, let me write it here. The next equation is it goes with this line, the third line. So it doesn't pick up pi 0, it picks up only pi 1. So I get lambda pi 1 minus lambda plus 2 mu pi 2 plus 3 mu pi 3 is equal to 0. And again, I put this back here, put this back here, and I get pi 3 is lambda cube over mu cube over 3 times 2 pi naught. So one can continue and one can see the pattern that the distribution is pi n is equal to 1 over n factorial lambda over mu n pi naught. This lambda over mu, where this is the birth rate, this is the death rate, this is given, this usually given this this symbol is the ratio of the birth over death, and it's also called the intensity or traffic intensity, because it's like how many are coming and how many are leaving, the ratio of that. So this, in terms of this, I can write it as pi n is rho n over n factorial pi naught. Now what is pi naught? Pi naught one can find because we still have to plug in this condition. The condition, it's a probability, so must sum to 1. And that gives you pi naught this is simply e to the rho. So pi naught is e minus rho. So this means pi n n factorial. So this is a Poisson distribution. What we have found is that the stationary distribution or limit distribution, the same, always exists. It always achieves a limit for this case, which makes sense because Because if you have a certain immigration rate and people are dying, then the rate of death actually slows down when there's less population. And it will then be just balanced out against whatever the rate of immigration is, and you will achieve a certain uh, steady distribution. On the other hand, if your immigration rate is very large and lots of people are entering, again you have a lot of population and then they start going to dying. But the lesson is that there's always a stationary distribution or limit distribution available here. Now, one can probably like general solution of death birth processes. So in the general case, what would happen? In the general case, in the death birth processes, all you are giving are is these numbers. There's no mu0, mu1, mu2, and so on. So that's it. That's the most general birth death process if you give these numbers, and it's not in general linear. The birth rate may depend on how many people are already present, and similarly death rate may depend on how many people are already present, depending on the condition of the population. The general one, the most general one, someone's mic is open, please close your mic. Who is this? So the most general one would be lambda naught, and here minus lambda naught, mu1, lambda 1, mu2, lambda 2, minus lambda 2 plus mu2, mu3, lambda 3 minus lambda 3 plus mu3. So this is a very simple structure. It goes like along this thickened diagonal, and over there, you know, mu2, lambda 2, in between minus of the sum of the two. So if one tries to build the stationary distribution for it, then the first one gives you and this gives you this. And if you try to build the next ones, like we can do it order by order, but the general one comes out to be this. It's just like what we did in the last example, just choosing particular values for lambda and mu. And these are all satisfied. One can see that the general solution is just like in the last one, we ended up multiplying all these guys. So one can see very easily that this equation is satisfied with this, and this is the only solution you have, because you can also see it by building it term by term. So as you can see, if I put pi n minus 2, I will have lambda naught up to lambda n minus 3, but then this will provide me lambda n minus 2. So I will have lambda n minus 2, and over here mu n minus 2. Similarly, over here, I will have all of these up to lambda n minus 1 and mu n, but mu n will be cancelled. So I will have mu n minus 1. And then this will be cancelled with this guy coming from here. And this will be cancelled with this guy. This will be cancelled with this guy. So it is satisfied. And, but then we will also have to have, so this is the general thing you will get. We will have to have this has to be finite for this to make sense as a probability distribution. So that would be the condition for this to be have a stationary distribution. Now, one example of birth-death process of its application is what is called the queuing theory. And in this queuing theory, there are various service problems. So what you have is you have customers enter a service station, maybe a fast food restaurant or something. One single server entertains them. So if the server is taking care of a customer, the new arrivals get into a queue. Now, there are various conditions through which you describe that what kind of process is. So when you write M1, it means that you have one server. And this means that the customer's arrivals are Poisson. And this means that the time the server takes to resolve or to serve is also Poisson, or because it's a single variable, so you can say it's an exponential. So these are Poisson process. So I have to give some weights. So let's say this weight is lambda is the weight of arrival. It's a exponential distribution. This is also as a weight. Let's call it mu. So average service time is 1 over mu. So this will actually be described by birth-death process. So remember, birth-death process is a continuous time Markov process where the arrows are only to the next numbered thing. So clearly, if you have 0 customer, you have a weight lambda that a new customer can come. And when you have 1 customer here, because there's a continuous rate of these customers coming in, you have same lambda. So this is exactly what I described as the immigration into the population. There's a constant influx of how many come. So there's a constant rate of lambda of births taking place, or in this case, customers entering. Now, the death rate in the other problem, we assume that it's proportional to how much is the population, because each person can die. But here, it's not. Here, it's like if you have 5 customers, there's a probability that the server gets done with one of them. He's taking care of, out of these 5, he's taking care of 1, and the 4 are in the queue. So he gets done with one of them, and then you take a jump back. And that rate is mu. So they're all mu. So what you have is again this matrix, because this was the most general matrix. But in this, there's a great simplification that all of these are same. So the stationary distribution you get here is this. So if you look from here, you have n of these, and they're all lambda. You have n of these, and they're all mu. So what you get is pi n is lambda n over mu n pi naught, or I can write it as rho to the n pi naught, where rho is lambda over mu, and then on top I have this condition. To infinity rho n, and this is equal to, and this has to be less than infinity, which will be true if rho is less than 1. So that means the rate at which the server finishes with 1 customer has to be higher than the rate at which the customers are entering into the queue. It makes sense. If they keep entering at a higher rate, then you're not settling into a stationary distribution. is just blowing up. And in this case, you can sum the geometric series to get this as your stationary distribution. Now, what you can have more examples of this queuing problem. For example, you can say that there is a certain probability if the server is busy, the entering customers they stay with the probability q. Otherwise, they just leave. They don't bother. So how will this chain change? Well, this is still mu because it's about how much time the server takes. Well, here the first one is lambda. The next one is lambda is the rate of arrival, but now you have to multiply it with the probability that they actually stay. Lambda q, and so on. Similarly, you can change these things slightly. For example, you can say what happens if there is a finite room. You can take more than a certain number of more than n people in. So mn1, let's say n. You have lambda, if there are more than n customers come, they just leave. So that's your finite limit. And again, this time it's a finite chain, so nothing much changes. All you have is that you have to, this time when you sum, you have to sum over only these n. And one can try to find what is the stationary distribution. I'm not going to do it right now. You can try it, or we can do it next time. Or for example, you can change the number of servers. What if you have, for example, 2 servers? What happens then? These are lambda. You have 2 servers, so any one of them can finish serving the first, and you will take a jump down. And as we learned, you have to sum their parameters. So 2 mu. 2 mu. When there is 1, this is just mu. So it's going to slightly change the sums involved. So cover more ground than this online things. Okay, let me stop here. I'll upload this and send you the link.